Greetings, everybody. Learning is a hobby here. I want to go ahead and go through the solutions to section 4.2 in Tao's Analysis 1 book. So that's what this video will be about. Let me bring up my solutions to the exercise set and we'll go through them. Okay, so 4.2.1 wants us to show that the set of rational numbers, the equality on the set of rational numbers, the way that we defined it, is an equivalence relation. So we have to show that the equivalence of rational numbers is reflexive, symmetric, and transitive. He does give a hint here. He says for transitivity, use corollary 4.1.9. So here's the proof. I should also say a viewer mentioned in the last video that it might be easier to say A/B rather than A/B, and that's probably going to be easier to say. So I'll, instead of saying that A/B here, I'll say A/B, for example. And I think it'll make this go a bit quicker. So let X, Y, Z be rational numbers, then X is A/B, Y is C/D, Z is E/F for some integers A, B, C, D, E, F, and BDF not 0. So in order to show that it's an equivalence relation, there's three things that we need to show: reflexivity, symmetry, and transitivity. So reflexivity is obvious. AB equals BA, right? If A and B are integers, which implies that A/B equals A/B by the definition. So that shows reflexivity. Symmetry follows. If we let X equal Y, then that means that A/B is equal to C/D, and those equivalence classes we said are equal if AD equals CB. And by the properties of the integers, since equality of integers is an equivalence relation, that means that CB is equal to AD, which implies that C/D equals A/B, which implies that Y equals X. So that shows symmetry. And then lastly, we have to show transitivity. So let X equal Y and Y equal Z, then A/B equals C/D, and C/D equals E/F, implies AD equals BC and CF equals ED. Then multiplying together here, we get ADCF equals BCED, which implies AF equals BE by corollary 4.1.9, which is cancellation, which implies that of cancellation for the integers, which implies that A/B equals E/F, which implies X equals Z, and that shows transitivity. All right. Next is 4.2.2, which Tao asks us to prove proposition 4.2.3, but I actually already did that in my summary for section 4.2. Let me just remind you of what that theorem was. 4.2.3 was this one, that the sum, product, and negation operations on rational numbers are well defined. So if you didn't see the last video, I proved that here, so I'm not going to do it again in the exercise set. All right, question 423 says prove proposition 4.2.4. Let me read that out and then I'll read his hint here. What was it? 4.2.4. All right, that's this proposition here, which is the laws of algebra for rationals, which is looks very similar to the laws of algebra for the integers, except here we're dealing with rational numbers, and we get that extra 10th property here, which is that if X is not 0, then X times its reciprocal equals its reciprocal times X, which is equal to the multiplicative identity on the rationals, which is the number 1. All right, so we're going to prove that here. He does give a hint. He says, as with proposition 4.1.6, you can save some work by using some identities to prove others. And I'll go through this kind of quickly because it's very straightforward. Most of these just use the definition of, how we add and multiply rational numbers and, reciprocals and so on. So I'll just, just very quickly go through these. Let X be A/B, Y be C/D, Z equal E/F for integers A, B, C, D, F, BDF non-zero. Then addition is commutative, which we can show just by, again, so if you take X plus Y and just use the definition, the way that we defined addition of those equivalence classes, and you look at y plus x and use the definition of what it means to add those equivalence classes, then you get that x plus y equals y plus x. It just follows directly from the definition, and also equality of integers. All right, part B is associativity of addition, and again, it follows directly from the definitions here. If you do the calculation x plus y first and then z, you get the rational number that we have down here, ADF plus BCF plus BDE double slash BDF, when you go through the calculation. And if next you do x plus and then y plus z, and you add those together using the definitions, you get the same number, which you can see here. So both of these are the same rational number because the numerators are the same number and the denominators are the same number, so it's the same rational number. All right, so addition is associative. Same idea for additive inverse. We don't have to worry about showing x plus 0 equals 0 plus x because we already showed that addition commutes. So we just have to show that x plus 0 equals x, for example, and that follows by the definition. 0, if you remember the section 4.2 when in the video, we defined 0 to be the equivalence class 0 double slash 1. Right. Part D is showing existence of additive inverses. And again, we don't have to worry about the commutative part because we already showed that addition is commutative. So we just have to worry about x plus minus x and show that that's equal to 0, which again, if you just use the definitions, follows directly from the calculation. Right. Multiplication is commutative as well. Again, so if you take x times y, you can, and then use the properties of integers, then you see that you get the same equivalence class as y times x, so they're the same rational number. Same thing for showing that multiplication is associative. Again, just use the definition and you'll see that they're the same number. Like I said, I won't belabor the point here. If you do want to see any of the the steps in detail, feel free to pause your screen and you could just look at them. Letter G, x times 1 equals 1 times x equals x. Again, don't worry about the commutative part because we already know that multiplication is commutative. We proved that in part E. So we just have to show that x times 1 equals x, which again follows directly from the definition. We get that x times 1 is x. So 1 is the multiplicative identity for the rationals. Okay, then we show distributive law. So if you look at x times y plus z and just do the calculation out, you get ACF plus AED double slash BDF. And if you do xy plus xz, when you simplify, notice that you get the same rational number. So that shows that multiplication distributes over addition. And we don't have to worry about proving I because we just proved the distributive law above in part H, and we also showed that multiplication is commutative in part E, so we get the part I here, we get that for free. Right, and then lastly, the 10th rule here, part J, the existence of multiplicative inverses, provided that x is not the rational number 0. So again, we don't have to worry about the commutative part because we already know that multiplication commutes. So I just look at x times its reciprocal and show that that's equal to 1. And again, just it follows directly from the definition. So that shows that all of those 10 properties are satisfied by the rational numbers. Right, 4.2.4, prove lemma 4.2.7, which I'll bring up here to remind you what that says. Right, this lemma is on the trichotomy of rationals. So I'll read it out just so it's clear what we're trying to prove here. Let x be a rational number, then exactly one of the following statements is true. Either x is equal to 0, x is a positive rational number, or x is a negative rational number. All right, so let's prove that. Oh, he gives a hint here, by the way. He says, as in Proposition 2213, you have to prove two different things. Firstly, at least one of A, B, C is true. And secondly, that at most one of A, B, C is true. So first, let's show that at least one is true. So let X be a rational number. Then there are A and B integers such that X is A /B, and we can assume here that B is positive, since if A prime /B is equal to A /B, that implies that A prime B equals A times negative B equals negative A times B, which implies that A prime equals negative A by cancellation in the integers, and that means that negative A negative B is equal to A /B, since negative A times B is equal to A times negative B by properties of rational numbers. Okay, so then by trichotomy of the integers, exactly one of A equals 0, or A greater than 0, or A less than 0 is true. We proved that in this. I think I did it in the summary for section 4.1. It was either that or in the exercise set. I forget now, but it was one of those. We proved it. So we can now use that to prove trichotomy for the rational numbers. So if A equals 0, then X equals 0 /B, which is the same equivalence class as 0 /1, which is the rational number 0. 2, if A is greater than 0, then we already assumed by hypothesis that B was greater than 0. Then by definition, that means that the rational number A/B, which is equal to X, is positive. And then finally, part 3, if A is negative, then again, by hypothesis, B is greater than 0, implies X is A/B is a negative number, again, by the way that we defined negative rational number. All right, so that shows at least one of those three properties is true. Now we have to show at most one of them is true. And I won't go through the details here. It follows from trichotomy of the integers. So for example, if you assume X equals 0 and X is greater than 0, then X greater than 0 implies that A is greater than 0, but X equals 0 implies that A is equal to 0, which contradicts the trichotomy of the integers, which we've already proven. And then same thing for X equals 0, X less than 0, that contradicts trichotomy of the integers. And also if X is greater than 0 and X is less than 0, that implies that A is greater than 0, A less than 0, which also contradicts the trichotomy of the integers. Therefore, at most one of them is true. And also we had previously up above that at least one is true. And the only way that can happen is if exactly one is true. Okay. For exercise 4.2.5, here they want Tao wants us to prove proposition 4.2.9. Let me bring that up so we know what it says. All right, this is this proposition deals with the basic properties of order on the rationals, and we'll do them one at a time because there's a bunch of them. Let X, Y, Z be rational numbers, then the following properties hold. So we'll do order trichotomy first, and we'll just go down the list. So part A says exactly one of the three statements: X equals Y, X less than Y, or X greater than Y is true. So let's go ahead and prove that. All right. So before we start, X, Y, Z are rational numbers, and let X be A/B, Y equal C/D, Z equal E/F for all A, B, C, D, E, F integers, where B, D, and F are assumed positive. Okay, so let's do order trichotomy. If X, Y are are rational numbers, then X minus Y is rational as well. Then by lemma 4.2.7, exactly one of X minus Y equals 0, X minus Y greater than 0, or X minus Y less than 0 is true, which implies that exactly one of X equals Y, X greater than Y, or X less than Y is true. All right, going on to part B, which is anti-symmetry of the order relation, which says one has X less than Y if and only if Y greater than X. And here is the proof. Let X less than Y, then Y minus X is greater than 0. Here, all these are double arrows. All these are biconditionals. So you can go down for the forward direction and up for the reverse direction, because it's an if and only if proof, right? It's a biconditional statement. So y minus x greater than 0 implies c double slash d plus minus a double slash b equals c b minus a d double slash b d is greater than 0, which if and only if cb minus ad is greater than 0, if and only if ad minus cb is less than 0, if and only if ad minus cb double slash bd is less than 0, if and only if a double slash b minus c double slash d less than 0, if and only if x minus y less than 0, if and only if x less than y. And that proves that the order is anti-symmetric. All right, next is order is transitive, which means if x is less than y and y is less than z, then x is less than z. Right, so here's the proof. Let x less than y and y less than z, then y minus x is positive, z minus y is positive, which means that cb minus ad is positive, and ed minus cf is positive, which implies here I can multiply through by f, so cbf minus adf greater than 0, and I can multiply the second inequality by b, so EBD minus CBF greater than 0. I'm allowed to do that, and the order is preserved because these are integers that I'm working with here, and we already know that the order of integers is preserved by positive multiplication, and I'm multiplying by positive numbers here. So, and then from there, that if I add those inequalities together, you get EBD minus CBF plus CBF minus ADF greater than 0. That again, that order is preserved because we're dealing with integers here, and we already have the properties of the order relation on the integers. Notice you can cancel CBF and minus CBF, and you're left with EBD minus ADF greater than 0. And then by cancellation of the integers, you can cancel the common factor of what is it? D, I think you can, cancel D from both sides. Then you get EB equal minus AF is greater than 0, which means that EB minus AF double slash BF is positive, which means that Z minus X is greater than 0, which implies that X is less than Z. Okay, that's transitivity. Then we have addition preserves order. So in other words, if X is less than Y, then X plus Z is less than Y plus Z. Right, so here it is. Let x less than y and z greater than 0, then obviously y minus x is positive, which implies that cb minus ad double slash bd is positive, which means that cb minus ad is positive, and also z greater than 0 implies e greater than 0, f greater than 0 implies e times cb minus ad positive and bdf positive. Again, we're dealing with integers here, so we are allowed to work with them, the order relation on the integers here. So that implies that E times CB minus AD double slash BDF is positive, which means that Z times Y minus X is positive, which implies that ZY minus ZX is greater than 0 by distributive law for the rational numbers. And that implies that YZ is greater than XZ, and that's it. Okay, and then this is the last problem here. It's a kind of a short exercise set, and then we can move on to the next section in the book. So question 4.2.6 says show that if x, y, z are rational numbers such that x is less than y and z is negative, then xz greater than yz. So here's my proof. Let x less than y and z less than 0, then y minus x is positive and z equals negative e double slash f for some E positive, and by hypothesis, we're assuming F is positive as well. Then CB minus AD double slash BD greater than 0 implies CB minus AD greater than 0, and also BD greater than 0, because both B and D are positive. Then negative E times CB minus AD is less than 0 because of the way that the order relation works for the integers, right? So when you multiply by a negative number, it switches the direction of the inequality, and BDF is positive. Then that means that negative E times CB minus AD double slash BDF is less than 0, or in other words, it's negative, which implies that Z times Y minus X less than 0, which means that YZ minus XZ is less than 0. Finally, which means that YZ is less than XZ, and that's the proof. Okay, so that's the exercise set for section 4.2. There's only 2 more sections left in chapter 4, which I'm hoping to get through within the next week or so, or at least, until maybe 2 weeks or something, but relatively soon. I'm hoping to get done with it relatively soon. I'm going to start on the summary for section 4.3 tomorrow, and then I think the exercise set for that is relatively short. The section summary will be a little bit long, but the exercise set is short. And then the following section 4.4 is relatively short, and its problem set is also kind of short. So we should be able to get through chapter 4 pretty quick, and then we can finally get on to the construction of the real numbers, which I'm looking forward to. So I'll see you guys in the next video. Please give me a like and subscribe. Let me know what you think down below, and I'll see you guys in the next one. Keep learning, everybody.